In this video, we are continuing on with our attempt to understand instructions from the sort of bottom up. So the last time we took the very broken down to the nitty-gritty idea of a simple instruction like load accumulator A, put a number into the accumulator so we can sort of have it near the ALU and do some math, um, and how that got down to sort of the ones and zeros, the actions or inactions of all of the various computer components. And now I just want to talk a little bit more, since we understand those steps in that process. Um, when we talked about the basic units of a computer, we said to be a computer, we needed input and output. We needed the memory and control and ALU. And then when we sort of sketch out a little baby architecture, we see those things, and we also see a bunch of registers. And registers play like a role like memory. They hold on to things. They're just a little like smidge of memory. Um, but they sort of help speed things up. We're interested in doing this computing as fast as we can. So we went from mechanical to electronic because it was faster. Um, and and that's another, we're always trying to be faster. And so one of the reasons that we have all these registers floating around is because they speed things up for us. So we know that we saw when we were mapping out those ones and zeros and really sort of parsing it down to the nitty gritty thing, then anytime we deal with memory, it's a two-step process. The got to get the address straightened out, and then you can deal with the data. So an addressing step where you're putting something into the memory address register. Now finally you're pointing at the value you wanted, you can deal with the data. So it's always, anytime we're dealing with memory, it's two-step: address then value, address then value. So that's one thing that registers bias, is that you can have instructions to say, this is only a temporary thing, throw it over into a register. And that's a one-step process. So that makes it faster than it's one step instead of two steps. But then the way things are really laid out in the computer is that if you're really talking about memory and not some cache, then memory is on a separate chip from the processor. And so there's also a question here with the speed of registers of their vicinity. They are on the processor chip, whereas memory is separate. So there's sort of like, I'm saying, like, there are two things: processor and memory. Sorry, the sort of registers that are on the processors, or next to the ALU and control, and then there's memory. Um, it's always more complicated than that. And there's another level in there called the cache. We'll talk about it another time. But while we're on to registers, let's talk about different roles registers play and how big they are and so on. And so a register can hold data, like the accumulator held the data that we're actually going to manipulate, so it was next to the ALU, so we could add them and subtract them and perform logic on them. We had address registers like the memory address register, and that tells you how many things the size of that can tell you how many things you can address. The size of a data register tells you how big your numbers could be or how precise your numbers are. The size of an address register tells you how many things you can address. And the size of an instruction register will tell you possibly how many instructions you can have. So these are important features in the architecture. So if we look, say, in Intel's sort of history, we see that, say, the data with the size of the register uh, sort of slowly building up, small back in the 70s, 8 becoming 16, 16 becoming 32. And then, certainly in my lifetime, the big change was going from 32 to 64. And you still see occasionally things that, you'll start some software package. I think if I start to write an R program, it often asks me, do you want 32 or 64? One of the big differences will be, again, in the address register and how many things you can address. So typically in memory, you address a byte, 8 bits. And then you have the address register will tell you how many different addresses you can have or how many bytes you can address. And this was a big change as we went from the 32-bit architectures to the 64-bit architectures. So let's just do a bit of math around this to see what 32-bit meant. A 32-bit register can have up to 2 to the 32 different combinations. So it can have 2 to the 32 addresses. 2 to the 32 is that big number. So you think that's a big number until you convert down to the units we're used to. So that is, what is that? Billions of bytes or something. But if we convert from a byte to a kilobyte, and then we convert, so that's, what are we dividing by? 1024 there, I think. And then we go from kilobytes to megabytes. That's another 1024. And then we go one more from mega to giga. And so in that, byte to kilo, kilo to mega, mega to giga. So that was roughly 1,000 each time. And so now we're down to 4 GB. Well, in today's computers, 4 GB of memory is pathetic. So we definitely, one of the big gains in the architecture when we went from 32 to 64 was that we could address more things, have bigger memory, and thus faster computers, because the amount of memory you have controls so much. The registers are a thing of the hardware. They are your lowest level language, your machine language will know about the registers. Most high level languages will not. C tends to be one of the exceptions, that some instructions in C will know about sort of low level things. And this is an example that might be familiar from either programming concepts or networking concepts of we are layering and we are information hiding. So all that information about the registers is important, and depending on the level you're working at, the layer you're working at, you might not know anything about it or need to know anything about it. And so now we're ready. So we talked about the hardware and the ones and zeros burned into ROM, and now we're ready to sort of talk about the software side, the lowest level. So we sort of came up from the hardware. We said, here are registers and ALUs, and they had these control pins. So we're coming down from the components of hardware. We filled in that middle layer of firmware, those ones and zeros burned into ROM to get the hardware to do what the software wanted it to do. But what is this software thing? Okay, so that microcode, those ones and zeros from the previous parts of this presentation are in ROM. But when we talk about software, the software is going to be in RAM. And we just sort of talked about, say, the memory address register and the its in significance in the architecture that the memory address register will tell us how many things we can address. Well, ROM is also addressable. So again, I have my weird little phrase that um, ROM is RAM, but RAM is not ROM. And that I mean that the acronyms ROM uh, means read-only memory, so you only have the one action of reading it. But the RAM, the acronym stands for random access memory. That means it's addressable. And ROM is addressable, so ROM is RAM. And so what we so when we want our ones and zeros to perform a particular instruction, and those ones and zeros are burned into ROM, what we need is the address of ROM of those steps to perform that instruction. And so now we're at our next line, our next level of code. Machine language can be thought of as the addresses of the ROM. So the ROM is burned, so the microcode is burned into ROM. So a given instruction, or the first instruction of that it needs to execute is at a particular place in ROM. And if you supply its address, then you are accessing that microcode in ROM. So then our opcode of our instruction can serve as that is a machine level thing. So we talk about the machine language, the instruction coming out, it has an opcode, an action part. We can think of that action as the address of the steps in microcode. So now we've got the connection from software through the firmware down to the hardware. So we are addressing this software hardware interface. So the machine code program, it will basically say it's mixing in some data as well, but the opcode part of it is saying go to this address of ROM. ROM is addressable. Go to this thing at ROM, perform the microcode. Go to the next thing. Then the next line of machine code will say go to this address and do those things. So the microcode, sorry, wrong thing. The machine code is basically a sequence of addresses of microcode telling you sort of go here and do that thing, go there, do that thing, with some data mixed in. So there were opcodes and operands. So these addresses are the opcodes, and then there's the operand, which gets moved around by those instructions. Okay. But the machine code is software. This is what makes it soft, which makes it easy to change. So the microcode was the firmware. It's sort of burned into the ROM. It's read only, or at least so you either can only read it, or you're going to change it not very often. Whereas the software you want to be able to change easily, and so that was in memory, which is RAM, makes it easy to write. And so how do we get our what makes it easy to change is that it's in RAM, but what is it that is in there, and how can it be changed? So this again, it's this in the what you can do. The instructions are in ROM, and they're not going to change, or not going to change very often. But the machine code is in RAM. It's software. It's more easily changed, and it is what can you do? The instructions are like what you can do, end of story. They're not going to change. But the software, the arrangement of those instructions and the data that those instructions are offering, acting on can easily be rearranged. And so that's what we mean by programming, sort of rearranging the instructions, rearranging the data those instructions act on. That's programming that's put in that software, that's put in RAM, and we can easily change the order. We can easily change the data. Um, and but our software that we're used to writing at higher levels has to somehow get down to this machine language where the code portion of it basically serves as the address of ROM, and it's ROM that knows how to tell the components of the hardware what to do and when to do it, i.e., to execute. And so our flexibility in programming are so the inflexible part is what the ROM can do, what instructions we have. But the flexibility of software is rearranging the instructions, different orders, and acting on different data. And so we are changing order, changing data. That's what we can change, and we make that easy to change by putting it in RAM, which is very easily read, but also very easily written. And we'll stop it here. Thanks for your attention.